Here, we can finally start to explore phase diagrams. Let's suppose that the two components are in equilibrium. So, the chemical potentials would then be equal. And we can write the expression this way. Now, in each component, there are two equations and four unknowns: temperature, pressure, component of A in alpha, and component of A in beta. If any two values are fixed, okay, say for instance we fix temperature and pressure, the equation can be solved to obtain the remaining two. What this means is that equilibrium can actually take place over a range of different temperatures or pressures. And in the above equation, for a binary solution, the composition is automatically fixed when temperature and pressure are fixed. So let's look at a 3D representation of this. Here, we have a three-dimensional representation of pressure, temperature, and the number of components of A. Within this three-dimensional boundary, equilibrium can exist. Let's now imagine that we take a cross-section of this boundary, like that, and keep pressure constant. So we assume an isobaric section when we do that, essentially isobaric conditions. And what is the isobaric condition that we usually assume? Usually, it is atmospheric pressure. That's 1 atmosphere. Why? Because most solid solutions are processed under this constant atmospheric pressure. So this figure over here shows that the two phases can coexist within this defined region at the following temperatures. So this graph is saying the exact same thing. The composition of alpha and beta can vary according to the temperature, but they can exist in equilibrium within this entire region. Let's now assume that there are three phases: alpha, beta, and gamma. When you want to express them, when they're in equilibrium with each other, the equilibrium condition can be expressed in this following set of equations. Notice that this is merely an extension of the binary equations. And here, there are 4 equations and 5 unknowns. By fixing one unknown, we are going to allow the remaining 4 to be solved. And this is rather important because temperature is unique, which we will show you in the next slide. The temperature here, which is common for all 3 phases, is something known as the eutectic point. So going back to our phase diagram, this is the eutectic point. The eutectic point is, of course, the point whereby all 3 phases can exist in equilibrium. Notice too that there are 2 other points here and here, which also represent an equilibrium point, whereby mixtures of phases can exist in equilibrium.